Hello, in this lecture we will get introduced to high performance computing. This is the agenda. First we will see the history of supercomputing, then we will see the need that exists for high performance computing, then we will see what are the components of a supercomputing system, and finally we will end up with the methodology that is used for parallelization. So, let us see how the computing began. In the year 1947, ENIAC was made with funding from Department of Defense in USA. Its basic purpose was to calculate the firing tables for projectiles that were fired by army. This was programmable, however, the programmability was made through the patches of cables that were connected to get the desired algorithm implemented. Since then, the speeds of top computers have increased over the years. Here in this diagram you see a section which is green in color, and that refers to operations per second. Operations per second refer to the integer operations that the computers could do in the 40s and the 50s. Somewhere here the transistor was invented and computers were subsequently built using transistors rather than relays and vacuum tubes. As a result, this blue line indicates the number of floating point operations that the computers could do, and a milestone was reached when the supercomputers exceeded the speed of 1 exaflop of performance. So, now let us see how the power of supercomputers is measured. So, as I mentioned in the previous slide, floating point operations in a second is the measure. So, if a computer can do one floating point operation in a second, then its power would be 1 flops or floating point operations per second. But 1 flop is a very low number. Typically today's supercomputers have got a capacity of teraflops, few teraflops, which is 1 into 10 to the power 12 operations per second. In the same way we have petaflops, that is 10 to the power 15, or exaflop, that is 10 to the power 18. Now, how do we know what are the top supercomputers in the world? That is maintained by a website by name Top 500, and the website address is www.top500.org. Now, how are the computers rated on this website? For that a benchmark is used, and that benchmark is called as high performance linpack. So, every computer which needs to be, whose performance needs to be submitted to this list, they need to run this HPL and find the best performance that their supercomputer can offer, and that is submitted. As a result, we get a graph like this. In this case, we have, starting from somewhere around 1993 till today, what were the speeds of the top supercomputer, that is ranked number 1, and the one that is ranked number 500. So, this arrow shows how the performance of the top supercomputer in the world has increased, and this band indicates what was the range of the top supercomputer and the 500th one in a particular list. This list is published twice a year, and a pattern like this indicates that a particular supercomputer remained on the list for a few times until another one came in and surpassed it. So, as of now, the frontier system at the Oak Ridge National Laboratory is the most powerful one, which has got a score of 1.2 exaflop when the high performance LINPACK was run on it. It may be pertinent to note that this kind of performance is achieved through close to 8.7 million cores that it has, which is a combination of CPUs and GPUs that are installed in this system. Moving ahead, let us see what is the use of these supercomputers. So, before that, we need to understand how science is being done today and how it was done in a traditional way. If you look at the traditional way, science began with a theory that was proposed. Like Newton said that there exists a force of gravitation that earth exerts on every body. Now, to prove his theory, he conducted experiments. It began with an apple falling on him when he was sitting under an apple tree. Once he proposed it, he made several experiments, and every time like he threw something in the air, it returned to earth, and he could prove it through repeated means. Thus, a theory is proposed, it was proved through experiment, and it is, if it is repetitive, then we call it as a science. And none other than Galileo made this statement that mathematics is the alphabet with which God has written the universe. What does it signify? It signifies that every branch of science finally has its roots in mathematics. Be it physics, be it chemistry, be it biology, or any branch of science you take, you will find that the fundamental aspects of that particular branch of science are easily explained using mathematics as its basis. If you look at the modern way, you still do science using theory, experiments. However, now we have another tool called as computation, which is done using computers. So, together science has got an additional aid apart from theory and experiment, which are bound to be there, which is through through computation. Thus, we have this branch of science now called as computational science, which uses science as a basis, and in every branch of science we look towards the mathematics and then use this mathematics with computer science, where the computations are done using computers, and a combination of all of this leads us to computational science. So, computers and particularly supercomputers deal with implementation of computational science in an effective manner. So, let us now see what comprises of high performance computing. So, it is a set of computing technology derived from the standard ones, which are used for specific purposes, which includes very fast numeric simulations, modeling, and large amount of data processing. And to make this happen, it makes use of what is called as parallel processing. This is at the heart of supercomputers, which is then used for running advanced programs which comprises of grand challenge problems. And it is employed specifically for those cases which require a lot of mathematical calculations. And as we saw in one of the slides, we are measuring the power of the supercomputer using the floating point operations that it can perform in a given time. To take it forward, it would be pertinent to say that supercomputers' compute power is harnessed to execute a few applications in an extremely fast manner. Please note that you cannot take just any application which is running on a desktop or a laptop and then say that I will run it at a fast speed on a supercomputer. No, it is not like that. You have to identify specific applications which can be run using parallel processing algorithms, and then they will run fast. We often use the term supercomputer. What is the definition of it? It is a system whose performance is very close to the currently highest operational rate for the computers. Like we saw today, Frontier is the top supercomputing system with 1.2 exaflop as its compute power. Then all the computers which are very close to it, and top 500 is what we know, which are the top 500s as of today, they all and few more will qualify as a supercomputer. We also saw that the power of computers, particularly supercomputers, is increasing day by day. As a result, a set of computers which are at the top range are called as supercomputers, and those which are less than that fade away. So, what we can say is supercomputers of yesterday do not remain supercomputers of today, and those which are supercomputers today will no longer remain supercomputers a few years from now. So, it is a moving target, and the top ones qualify to be called as a supercomputer. As we had mentioned that parallel processing is the basis on which supercomputers operate. So, the principle on which the supercomputer operates is that you use supercomputers to solve large problems. When these large problems are to be solved, they are divided into small problems, and these small problems are assigned to CPUs which are then solved concurrently. The important thing here is concurrency. If concurrency does not exist, meaning you have divided into smaller ones, but output of first program becomes input to the next one, then the concurrency is lost, and then such kind of applications may not be suitable for running on supercomputer. So, parallel processing is the heart of supercomputers, because you can make use of multiple processing elements in a simultaneous manner, and these processing elements are using the small problems in which the main program has been divided into. Another term that is sometimes used in conjunction with parallel computing is distributed computing. The principle is same, but instead of processing elements being closely bounded, they are in this case isolated. An example could be, in a lab there are, let us say, 50 computers and they are connected using gigabit Ethernet LAN. You can very well use this kind of setup to do distributed computing, which essentially would mean parallel computing. Having said that HPC can do something big, let us see where all HPC can be used. It can be used in day-to-day life. For example, weather forecasting and early warning systems for floods and other natural calamities is what high performance computing used for. Similarly, designing of new drugs, finding vaccines is something supercomputers is also used extensively. Then in science, one can use for designing new materials by investigating the electronic structures of the current material. In astrophysics and astroscience, one can use it for getting imageries and then analyzing them and exploring the universe. Similarly, in engineering, it is very much useful for doing simulation of a product before it is manufactured. In civil engineering, it can be used for, once a structure is designed, analyzing that structure and checking out its stability, its strength before you actually go for construction. Now, let us take specific examples. In science, we have two examples, in atmospheric science and in life science. In atmospheric science, the weather forecast that you see in the evening along with the news is done using supercomputers. That was the traditional application. However, now the same high performance computing is also used for investigating climate change, how it is happening, and then finding ways and means of combating it. Similarly, air quality due to pollution is another area where humanity is trying to fight it, and making sure that the air quality is improved once we know how it is deteriorating is another application where HPC is used. The life science reached a big milestone when the genome of human being was sequenced. This was a global effort, and no doubt high performance computing played a big role in achieving this. Genome sequencing will help in various ways to humanity, like designing personalized medicine and so on. Designing a drug for a disease or a new virus is something that HPC is very good at doing, and the best example of this was finding a vaccine for COVID-19 a few years ago. And one of the reasons why we got the vaccine in a record time, because most of the supercomputing systems in the world at that time were dedicated for COVID-19 research. Coming to engineering, there are few very good use cases. First is simulation of crash. The traditional way was designing an automobile, building it and crashing it, and then finding out which elements in the car are vulnerable and then fixing them. However, today all this can be done through simulation, and once the design is made, it is simulated on computer, and once the design is found to be safe, the cars are manufactured and a couple of cars are crashed just to validate the design, thus saving time and money in life cycle of a design of a car. Similarly, for aerodynamic simulations are used for design of aircrafts and missile. The essential problem that it is solved is a solid is moving through a fluid, and which also applies to submarines moving in water, and the computational fluid dynamic techniques, the mathematical modeling of that is used to design a structure which will flow through this fluid with minimal resistance. In civil engineering, structural analysis extensively uses HPC, because once the civil structure is designed, its validation is done through computers, and the technique that it uses is called as finite element method or finite element analysis. This can be used for improving the design of the structure so that it can very well sustain internal and external forces. Now, let us look at the components of a typical supercomputing system. This diagram shows one of the popular architecture which is called as a cluster. So, the important elements in this cluster are: first, the compute nodes. A collection of compute nodes gives you the compute power. As we have seen that parallel processing is an important aspect, and that is what is implemented in these compute nodes. These compute nodes are supplemented by what are called as a number of accelerated compute nodes. So, this contains accelerator. What are accelerators? Graphics processing units, general purpose graphics processing units are installed in these accelerated compute nodes, and they use single instruction multiple data, that is SIMD architecture, to accelerate certain workloads. Now, all these nodes are connected using a switching fabric. This red line here shows the primary interconnect, which is Paramnet or InfiniBand or any other such network, which provides high bandwidth, low latency transfer of data between these compute nodes. This is supported by a parallel file system, which consists of large number of rotating magnetic media like hard disk, which allows big files to be stored, and a parallel file system allows multiple processes running on these compute nodes to access the same file in a manner such that part of a code will operate on part of the file. Together, all the processes running on these compute nodes are going to operate on the complete file. The storage acceleration contains SSDs. So, this will keep the frequently used code and data which is taken from the hard disk, but provided to the compute nodes in a fast manner. Traditional use of tape libraries and backup servers allow the data to be backed up and restored from the parallel file system and the home area. Such a big cluster, when it is to be used, it has to be managed using boot servers and management nodes. Boot servers allow the compute nodes to be booted over the network, and management nodes allow the system administrator to manage all the elements in this cluster. The users are sitting here in the local or remote network. They land up on the cluster through this gateway which contains firewall, and login nodes is where they get the prompt. So, these cluster uses Linux as an operating system. The users logs in using his credential and then subsequently submits a job. The jobs are run on the free compute nodes and the jobs are completed. Such a complex computing system needs an appropriate software stack. It begins with an operating system. Linux is the preferred operating system. It is a stripped down version which contains just the required elements. CentOS 7.x is one example. One can use Debian or Fedora or any other version of Linux. Then there is a middleware. The middleware consists of cluster monitoring tools like Ganglia, which tell which nodes are free, which nodes are available. Then when the user submits a job, it will make use of provisioning tool like OpenHPC to assign the free nodes. The file system consists of two parts, NFS which will have the home area and Lustre which is the parallel file system. These are used when the programs are running. The code and data is loaded from NFS. The scratch data which is generated during running of the code is uses Lustre. And finally, Slurm is the job scheduling software to which a user submits a job, and Slurm in turn will use the provisioning tools to assign nodes, which in turn will use the cluster monitoring tools to know which nodes are free. This is the middleware, and at the top are the programming tools. In a typical program, you use a compiler, linker, loaders. Similar things are available here. However, because it is a parallel framework, you need things like libraries like MPI, you need development tools like which could be open source or specific to the Intel platform, and finally you have the performance monitoring tools which will help you in identifying the hotspots in your program, which you can then take care of in order to improve your performance. So, a cluster supported by a HPC software stack gives you the complete solution on which users can develop parallel programs, run them and improve their performance. To recap, you have the processors which are at the heart, a large number of processors each having multiple cores. Then they are supported by memories. The memories contains code and data which are used while running the program, and the exchange of data between memories of processors is done using system area network like InfiniBand and ParamNet. Then additionally you can use accelerators or co-processors which can accelerate some of the typical workloads, and all of this comes from the storage subsystem which consists of hardware and software, which in general gives a parallel file system for speeding up the programs that are run on the supercomputer, and it is ably supported by operating system, compilers, the standard system software tools, and for parallel processing frameworks you can use MPI or threads or a combination of this, and finally once the program is running correctly, it can be analyzed, tuned, debugged for scalability, for improving performance using appropriate tools. And finally, if you are a domain expert, you can simply use the available application softwares. Now let us see how it physically all this thing looks like. So, this is housed in a rows of racks. As you can see here, you have a rows of rack, each rack having multiple nodes in it. So, this is one rack. So, in this case there are 8 racks that you can see which are stacked next to each other. What goes inside this rack is a node like this. What is this node? This node internally contains a motherboard. This is a motherboard which can take 2 sockets. Each socket can take one CPU, like in this case Intel Xeon is used here. This will have memory which will go into all the such sockets which are blue in color. So, CPU, memory, and third thing is the I/O. In this case we have shown a network interface card which allows us to connect to the switches. So, CPU, memory and I/O, these are the basic elements, and a large number of this which goes into the rack, and multiple such racks connected together using a system area network forms a cluster. So, having said this, let us see why we use parallel computing. The basic idea is a single CPU system has certain limitations. What are these limitations? One is that they are slow. As a result, your program can run, but it may take days, weeks or maybe more. If you take more CPUs, you can divide the job into multiple smaller ones, assign them to this CPU and get it done fast. So, the first advantage is that we are getting the job done faster. Second issue that we face with a sequential system is they are slow. The memory that they have is limited, so your data may not fit it. But if you have more CPUs, each CPU has got its own memory, cumulatively you get more memory. So, together what can be done? Either you can save time or you can solve bigger problems, or the third option is you can solve bigger problems in a shorter time. So, how does one make use of HPC? For that we are saying that we are solving grand challenge problem. So, these grand challenge problems are identified by domain expert, like you may have experts who deal with the domain of weather. They know the algorithms, they know the mathematics behind it, they know how the algorithms are going to work. They have to be teamed up with computational experts. The computational experts are good at making use of the cluster or the supercomputer that they have. They know how to make use of tools, they know how to convert the ideas into programs. So, together they will develop HPC aware software which will essentially be parallel in nature, which can solve large problems, which can solve problems in a quick manner. So, it starts with an algorithm conversion into a parallel algorithm, then converting this algorithm into code using higher level language like C or Python or any such language. Then once this program is written, it has to be compiled using one of the parallel programming frameworks. OpenMP, MPI are the examples of such frameworks. And then once the program is developed, you can further go and develop workflows or problem solving environments which the domain experts will use. So, the domain experts get insulated from the underlying hardware and the parallel programming frameworks because they get to use a GUI based program which they can use for the purpose that they want to. And some of these applications are available in open source, some of them are proprietary like MATLAB, so they have to be paid, bought and used. So, what is the methodology that is followed for parallelization? For that we need to understand what are the desirable attributes for parallel algorithm. First and foremost is concurrency. If your program and the algorithm cannot display concurrency, then such a program or such a algorithm is not fit to be used on supercomputers, because supercomputers derive their power by having multiple processing elements which have to be used simultaneously. Second is scalability. You can start with a small number of processing elements and then scale it up. So, if you can keep adding more number of processor and the algorithm scales up, it can use the available additional compute power, then it is a good attribute to be used for parallel algorithm. Data locality, this is useful because if the data that you want is available in the memory of the processor on which the code is running, it will obviously run faster than getting the data through a communication network which is present in the memory of another CPU. And finally, modularity, this is applicable to any program that you write, because then you can develop the programs in a modular way, combine them and debug them in a much easier manner. To aid development of parallel programs, certain parallel programming frameworks are available. The first one is OpenMP. So, this will work on only one node. Like I showed you a motherboard with 2 CPUs and multiple memory DIMM modules. On one computer like this, OpenMP will run. How do you invoke it? It is invoked through compiler based directive. Hash pragmas is what you use in your source code to parallelize those portions of your code which can make use of OpenMP framework. And running a parallel program on one node is not what one aims at, it has to be done on multiple nodes. For that you have a message passing interface or MPI. This is well suited for distributed memory computer, that means you have a cluster of nodes each having its memory, and across the nodes you use message passing. For this you have libraries which have to be linked to your code that you have written. These days use of accelerator is very common, and for that we have OpenACC as one of the frameworks. So, this is used only with those computers that have got accelerator attached to it. Again, this is compiler based directives can be used for invoking OpenACC primitives. So, to sum up, we have seen that HPC is in use in our day to day life, but a common man may not know about it because many a times it is working silently, like weather forecasting, etc. HPC makes use of parallel computing. This is the heart of HPC. You have to have an algorithm which is parallel in nature. Without that, it is not a good algorithm or a good program to make use of HPC. Today, clustering is the most popularly used method for connecting nodes, and for that you need a communication network like Paramnet or InfiniBand and a complementing software stack which can make all these nodes work together by making use of a parallel computing framework. And for that you need large number of compute nodes. Some of them are CPU only, some of them additionally have GPUs. And you have certain parallelization paradigms wherein you convert the idea into parallel algorithms and then write parallel codes, and parallelism is what gives you the performance. And for that you have multiple frameworks like MPI, OpenMP, OpenACC, CUDA, etc., using which you can write parallel programs and extract performance from a supercomputer, of which cluster is the most popular architecture. With this we come to end of this lecture. Thank you very much.